Thanks, Lee. Good morning, one and all. I'm going to briefly talk about, for about 20 minutes, maybe quicker, I can speak rather quickly, about aquaplaning in general terms. We're not going to have the definitive discussion on aquaplaning, but it does help with a bit of understanding for designers particularly, but even when we have identified problems on the road network, you can then assess it and get a bit more of an insight of what could be happening. And then I want to finish off the session with some of the problems we have with our current methods of assessing aquaplaning and a little bit of excitement of where we are heading. And what you've just seen from Bill's session is a bit of an indicator. So what is aquaplaning? Just as an introduction, to stop or to steer a vehicle on a road, the tyres must grip the road surface. Pretty understandable. Now, this grip is achieved by means of friction between the tyres and the uppermost particles of the road surface. Now, friction available is insufficient to resist the forces of acceleration, braking and cornering. The tyres may slip over the road surface. Now, in dry conditions, typically everything's okay. It's with the wet conditions that this friction is greatly reduced and problems can start occurring. Now, tyre tread and pressure, road surface and the geometry of that surface, vehicle speed and the depth of water all play a part or influence effective friction. So what is aquaplaning, or if you come from somewhere else up in Australia, hydroplaning? Aquaplaning occurs when the vehicle's tyres are separated and partially or fully from the road surface by a film of water which results in the loss of control of the vehicle. Now, the effect of aquaplaning on vehicle handling is directional instability. Also, braking becomes impossible. There is a very old video available from some testing that was done in Britain many years ago where they loaded a tyre up onto a drum, rotating drum, spun it up, they put about 800 pounds of pressure on that tyre, so it was simulating a vehicle on a road surface. They then sprayed water into the area between the tyre and the drum, and they kept pumping the water into it. It got to a point that the wheel started to spin down, but the drum kept spinning. So in other words, the tyre and the drum had separated. Now, workplace health and safety nowadays would have stopped the next bit because the operator of the equipment actually walked up to the high-speed rotating drum, put his hand on the wheel and stopped it from spinning completely, but the drum kept going. Nowadays, there'd be a major inquiry. Technically, there's always the layperson or the easier definition, then you've got the technical definition. Aquaplaning is the build-up of hydropressure beneath the tyre to the extent that it partially or fully supports the tyre and the load that's put on that tyre, separating it from the road. There are two main types of aquaplaning. There are a couple of others, but we'll just talk about the two main ones. The first one's viscous aquaplaning. A little bit of a mystery, so to speak. It can occur at very low speeds, but particularly where the texture, and we'll talk about the micro texture of the road surface, and I'll explain that a little later. We're talking about really smooth roads here. Can occur at water film depths as low as 0.1 of a millimetre. So we are talking about that's basically a wet surface. Because the mechanism is dependent on the viscosity of water and not the depth of water. Now, this is likely to occur during braking, such as an intersection. And it's a bit difficult to tell whether it's actually a skid or viscous aquaplaning, apart from one thing which I'll explain again later. The one that we're more interested in is what they call dynamic aquaplaning. It's the partial or full separation of the tyre from the pavement under flooded conditions. Now, what do we mean by flooded conditions? Well, we're talking about now this thickness of the water film, and we make so that it gets thicker as the rainfall falls. Now, at a given speed of the vehicle, the combination of tyre tread and pavement macro texture, I'll explain that in a minute, is incapable of discharging the water from the contact patch. So in other words, it's just built up and we can't get rid of it. So under full dynamic aquaplaning, virtually no part of the tyre will have any contact with the surface, and even though the vehicle is travelling at great speed, the tyre can be fully locked. You can't steer the car, you can't accelerate, you can't brake. It's just like on ice. You just keep going in the direction that you lost contact at. Fortunately, full dynamic aquaplaning is likely to be rare based on the current fleet of vehicles we have on the road, the tyres, and them operating within the normal speed limits, and also tyres in good conditions. It is important to note that in Queensland, the legal limit for your tread is 1.5 mil. That's actually too low. you should replace their tyres a little bit earlier than that. Partial dynamic aquaplaning is more likely to occur. Its loss of control may occur with the change in speed or direction as high demands on friction are placed. We're looking at longitudinal and lateral. The pavement doesn't know which direction the tyre is going, so there's a certain so-called bucket of friction there. As a car's driving along, it has longitudinal and lateral requirements, and it just takes out the bucket for both of those. So if one gets used too much, for say longitudinal, there's not much for lateral, the car starts slipping sideways. Now it's important to note there is a difference between aquaplaning and skidding. As I sort of alluded to this earlier. They're not the same condition, although they're very confused with it. In a skid, the tyre still has contact with the road surface. Friction is reduced to a point where slippage over the surface occurs. So typically then on a straight, a skid results from hard braking. It can also occur from hard acceleration. On curves, the vehicle may slip or skid over the surface and track wider than the steered path, so the vehicle starts to spin, go wider, or alternatively, the usual yaw condition where the back wheels try and catch up with the front wheels and you go sideways and the car usually ends up on the inside of the curve. So skidding is the tyre is actually on the surface, there is some adhesion, there is contact. In the dry weather you'll get a nice big black mark on the road. In wet weather the black mark is sort of there, there is rubber left behind but it's not as noticeable because of the wet. But the main thing is that there is some adhesion, the tyre is there. In aquaplaning, the tyre is completely separated, there's nothing left behind. Now in partial aquaplaning, part of the tyre is supported by the water, part of it's actually still on the road, so that part that's on the road is probably skidding. So partial aquaplaning is a half skid, half aquaplaning type situation. Now you can understand why it becomes a bit confusing. You find a lot of police and witnesses get confused between an aquaplaning situation and a skidding situation in an accident. If there's a bit of water on the road, and particularly if there's a little bit of a film, they'll just automatically blame aquaplaning. Not saying it's not the case, but it could still be skidding. Causal factors. It's always important to understand what causes aquaplaning. Road geometry. I like that's a bit funny, but we'll get to it. Road surface texture, porosity and rutting. Some pavements do have pores through it, open grade asphalt, etc. Operating speed is critical. Rainfall intensity, the water film depth that's built up. The tyre tread depth, the vertical load on the tyres. That's why trucks don't aquaplane as often. They've got heavier loads on their tyres. Tyre pressure is also important. And driver behaviour. It's surprising. The number of drivers that actually drive on their roads, they don't actually understand or identify that there's a film of water on the road. As long as they can see, they keep their speed up, and that's where some of the problems come on. Now this listing that you can see gives you an indication of the problem we have in actually defining strict design rules, because it's not definitively one over another. Now the road geometry and the road surfacing are the two factors that road designers have the most control over. Most people probably in this room are the designer of the road, not so much the surfacing. So aquaplaning is actually considered more of a geometrics issue than a drainage issue. Yes, it's in the drainage manuals because of the hydrology component of it, where you're dealing with rainfall and trying to determine film thicknesses, etc. But it is a geometrics issue. And why? Is the shape of the road surface has a direct influence on the stormwater runoff over the surface. It controls how long it stays on the surface, it controls how far it can travel, it can actually determine velocity and all sorts of things. So it directly influences the aquaplane potential. So when water film depths exceed acceptable limits, the problem is best solved through adjustment of road shape, or more correctly, the geometrics. So that's why when you have a problem, it's basically go back and review your geometrics, and that's why it's more important now to solve your aquaplaning potential problems very early in road design process. Get rid of them first and then fix your alignments, and then you can build the rest. If you've got to go and change it later on because you forgot to do it or some problems have come up, it's very hard to then alter the whole design. It takes too long. I'll talk a little bit about road surfacing because it's obviously an important part of the equation. Road surface properties cannot be developed to compensate for extreme weather conditions, excess speed or any deficiencies in the area of the geometrics. Two main characteristics of the pavement that we're really interested in is what they call the micro-texture, which is the actual top of the stone aggregate that pokes up, and the macro-texture. Macro-texture is the gap from the top of the stone to the top surface of the binder, and it leaves a small gap there. You'll also hear a term, the texture depth, or the average texture depth. That's a measurement of your macro-texture. What are these? Well, macro-texture provides drainage paths for the water to escape from beneath the tyre, in addition to the drainage paths provided in the grooves or the tread of the tyre. And it contributes to the friction, which we've already talked about, between the tyre and the road through what they call heuristic deformation of the tyre. Micro-texture has to be provided to enable the tip of the stone to penetrate any water film and provide adhesion with the tyre. So that's why the two work together, and I'll bring that together in the next slide. So we've talked about the road, which we can do something about as designers. The tyre we don't have as much control over. So we look at the road-tyre interface. The required friction that I've already introduced you to is generated at the tyre-road interface, or what's more commonly known as the contact patch. And this is the area where the rotor is actually in contact with the road. The two primary mechanisms responsible for the friction coupling at the road-tyre interface are surface adhesion and hysteresis or deformation. The technical name is, sounds like a disease or something like that, so we tend to use the word deformation. The adhesion is the actual slippage of the vehicle tyre over the stone, so it grips on that way. The deformation is where the tyre actually sinks down over the stone, and there's friction loss in that component. So in wet conditions, as the tyre rolls over the pavement surface, so if you can picture this in your head, tyre rolling over the surface, the water on the surface is displaced from the contact patch via three main pathways. Like a boat pushing through the water, you create a bit of a bow wave, so the area in front and to the sides, the water's pushed out that way. The void's created in the tread of the tyre. That's obviously a void that they can get. And as we've mentioned now, the void's under the tyre created by the macro-texture of the surface. And the two images there will show you those voids. The one on the right has got green tinted water to just show you that you can have a water film thickness with the stone sticking out. So as I mentioned, vehicle speed is critical. As speed increases, a point is reached where the surface water cannot be displaced from the contact patch. If you think about it, water to move is a function of time. The faster the rotation of the tyre, the less time you have for that water to actually move. It gets trapped. It can't get out to a void quick enough. And if there's less voids, there's less capacity. So the water's got nowhere else to go but sit in front of the tyre. So this wedge of water, they call it, builds up and continues to build to a point where the hydropressure is enough to actually lift and support the vehicle. And it will stay there until the vehicle slows down or the water dissipates and thins down, and then the adhesion or something like that can grab on again. Skid resistance. We hear a lot about that nowadays, and there's vehicles and testing equipment that can actually go out and measure the skid resistance of the pavement. So there is an implied relationship between aquaplaning potential and skid resistance, although there is currently no established direct link. So we can't take information from one and plug it into the other and vice versa. So unfortunately for now, but I know there are efforts to try and get a better linkage, we can use skid resistance tests to provide us background information when we're assessing aquaplaning potential or an issue that's actually occurring on the road surface. A bit hard to test skid resistance if a pavement hasn't been built. So now we've talked a little bit about aquaplaning, hope you've got a bit of an understanding of what's going on. How do we assess it? It's a bit of a simplistic process at this stage. So we use a two-part process. Firstly, we've got to determine what's this water film depth, particularly in the wheel paths. The road surface is actually quite a wide area, but you've got a fairly good idea where the wheel paths, or the majority of the wheel paths, will go. So they're the areas we're trying to target. And we're looking at over the whole pavement. It's really important when you get into ramps, interchanges, intersections, even roundabouts, etc., because you've got wider expanses of pavement that can capture water and direct it. And wide flat pavements like the motorways, etc. We then check the operating speed of the road section to work out what vehicles will operate on, and that tells us what sort of film depths we're looking for. If it's unacceptable, then we need to adjust. Which I think, no, doesn't matter. So now, Lee mentioned that our drainage manual is the gospel. I wouldn't say it is. It's just the way that we've reviewed and accepted the research and the data that we have. And what we've done is, we've had it now for quite a number of years and we're continuing to use it, is the method to work out the water film depth is the Galloway method, or the Galloway formula as it's more not commonly known. Galloway first started this back in '71, he did a paper back then, tested a number of surfaces, and then in 79 he got together with another group of people, or a few of them the same, and they tested a few extra surfaces and expanded the data set to develop the formula. And that's the formula. So D is the water depth, T is the texture depth, so it doesn't matter what the pavement is, if it's a concrete surface, a chip seal, or an asphalt, or mastic stone, whatever, they're measuring the texture depth of those voids that the water can escape from. Length of the path is obviously important. The longer the path, the more water build-up you can have. Rainfall intensity is critical. And S is the slope of the drainage path. Now, I'm not really going to go into explaining too much further there because I want to sort of wrap up and head in towards the exciting stuff. But it's important to understand the limits or the basis that the formula was developed on. And I'll explain why. Here's a picture of a flow path. This is typical of what we're trying to do. The road usually the paths, the long ones particularly start somewhere in the centre of the road. They'll swing out towards the side, but usually because of things like super elevation and even grade, the water actually, before it gets off the road surface, can actually turn and come back across the surface and go right across the other side of the road. So in this situation, you can get quite long flow paths. So what's the basis and limits of the Galloway formula? Well, it's an empirical formula for a start. So a number of tests were done, a number of measurements were created. They've used various statistical analysis processes to come up with a formula that fits that data so that they can predict. One of the main concerns is all the testing was done over a flow path of 48 feet, 15 metres. We're using this formula to predict the film depth up to 90, 100 metres away. So we're extrapolating way beyond the test data that developed the formula. He tested rainfall intensities up to basically 50 millimetres per hour. Slopes up to 8%. We have used it to assess slopes greater than that. He did look at several surfaces. The flow path that he tested over was a simple planar surface. There was no change in grade from top to bottom. And some of the criticisms of the formula is it doesn't contain a term for hydraulic resistance. There's no Manning's N or Horton's N or something like that in the equation. However, because it's an empirical equation, that resistance is sort of built in, and the texture depth is possibly not directly related, but a way of allowing for it. The method is one-dimensional. You know a little bit about 1D, 2D, and now 3D assessments. So it only assesses the depth of flow along a single zero-width flow path. Flow velocity, width and spread of the flow is not assessed. And also there are situations that can occur where the water runoff from off the road joins the road or on the road surface being fairly flat-natured. The boundaries between different flow paths and catchment areas is quite small. So if you get a bit of a build-up, it can easily jump across to the other flow path. So the Galloway formula can't really assess that properly. Just take a quick mention of the slope. Because we have predominantly more complex slopes or multi-sloped flow paths, Galloway's formula has an S in it, and that's a single slope, basically point to point from start to end of the assessment process. It's got a single slope. So what we need to do is use the best representation we can of a multi-sloped flow path and turn it into one single slope to assess, or at least from the start to the point of assessment if you want to work out a depth halfway along your flow path, which we traditionally do. The best single slope representation of this is what's called the equal area slope or the weighted average slope. The point-to-point isn't really that good. The diagram at the bottom, it's a little bit hard to see. There's a yellow line that goes from the very top, about the 1.5 mark, right down to the 0, 0. That's point-to-point. It's a much steeper slope. On this case, or it's giving a much steeper slope, whereas the equal area slope, which is the pink line, or the purple line, is a lot flatter. And that's more representative because this flow path is predominantly flatter. It has a short, steep section. So that's what we're specifying from now on in the manual. The new manual is about to come out. In fact, after this session and after morning tea, I've got to go back and finish the chapter off and then get it organised to be released. So that's how close we are. We're specifying this one. There is another slope that's been around called the equivalent length method. We've assessed that method. We believe it's flawed. There's a problem there because it doesn't properly account for the change in the flow at each point. So we're not allowing it to be used. We're just accepting the equal area slope, and that's all. So flow paths, this is typically a road. You can see the direction of travel. It's a right-hand curve, and this is the point of super elevation being applied, as you can see by the contours. So here's the flow path across here now. And we would assess that. As I said, you look for the wheel paths and you're testing for those. But it's also important, there's a flat section or relatively flat section there, and it's a subpath. And quite often you can just test that section alone. If you've got a problem there, then the whole flow path's got a problem. Or if it's very close in that subpath. So if you want a quick analysis, you can look. Just apply Galloway over that section only, and if it's very close to the limit or exceeds it, then your whole flow path's got a problem. So you don't have to do a lot of calculations, or unless you've got a spreadsheet set up to do it. So just quickly now on aquaplaning potential, because I'm running out of time and Catch Sim's going to chase me around the floor. Research indicates that full aquaplaning is not likely to occur for vehicles travelling about or below 80 to 100 kilometres an hour, provided the tyres are in good condition. Increasing water depth reduces the friction coefficient, with the greatest reduction occurring up to 4 millimetres. After that, the rate of reduction drops right off. So while it's not completely possible for us to define the recommended design limits for water depths, it has been suggested that the critical depth to cause aquaplaning occurs at around about 4 millimetres and above, particularly at the high speeds. Partial aquaplaning can commence at depths of 2.5. And the standards that we've adopted and put into our manual sort of hinge around that understanding. So I just want to quickly wrap up and join into this exciting bit of work that we're doing. There's a case study here. We've got a section of Bruce Highway just north of Mackay. There was we had a new job that was built, and not long after it was built, there was a number of rainfall events, and we had a number of reported aquaplaning accidents. They said whether they were truly aquaplaning or skidding, we're not 100% sure. One of them I feel was because the car did end up on the inside of the curve. But it was witnessed that large sheet flows across the left-hand curve at the super elevation point were occurring. Now we sat down, we used Galloway to assess it, and it was saying you're pretty well right. You're on the limit, but you could be right. We also used a few other things because there's a curve and channel there, there are other flows, and basically the old gut meter said something's not right there, this is what could be happening, but we're finding it difficult to assess. Here's the picture of the flow path. As you see, we're standing probably on its rightmost. It does come from underneath the wire rope guardrail there, but you can see it about mid-picture flowing across in front of that car. And this is after a main rainfall event, so it's pretty well drained off, but there's still some flow there. If I step back a little bit, you've got this drain. This is coming down about 7 to 8% slope, standing behind the photographer. Most drainage would come down and then swing to the right and go off to that little turnout of water. They've even put a little bit of an asphalt levee there to try and catch some of that water and get rid of it. If you look ahead to the wire road, you can actually see a bit of a sheet flow across it and how it's starting to turn and head back left. So our feeling was that the water was coming, a bit hard to show, but it's coming from the left-hand side, goes out under that road and then comes back again. That's the path we can assess easily with Galloway. But my feeling was that there was enough flow coming down that curve and channel and wide enough with enough velocity that it was actually going, some of it was going past that little levee, not turning right and going off, and joining that other flow path and continuing. But as I said, it was very difficult for us to actually assess it. So now I'd like to introduce 2D modelling. which Bill's already talked to you about. Combined effort between 12D Model, Bill Simon, who owns Two-Flow, but developed it, and ourselves, we started saying, well, can we actually 2D model a road surface to better understand the water flow across it? It hasn't really been done before. The power of a computer and some of the understanding has been the stumbling block. But Bill's actually done quite a bit of work on it and believes it is actually possible to do it, so we're heading down that path. This is a little bit of a picture of that situation. Now, the area of interest there I circled, that's actually that turnout that goes to the right, and where I reckon the water is jumping the boundary and going off to the left. So the next slide will be the animation of the model. Now, the red lines there is the build-up of water. The bigger the arrows, if you can see it, is the velocity. And you can actually see what happens. So the rainfall's building up. You can start seeing that flow coming down. Now starting to leak a little bit across and then bang, sheets across. And you can see also how wide that water's sheeting across. So vehicles going through that could easily lose control. So that was, there's a lot of work to go. We're able to assess for a variety of situations there. What we did from that is we spoke to our people in Mackay, look at some remedial action. So there's the before shot. The best thing we could do was apply a coarse aggregate sprayed polymer seal. That gave us a lot of texture. The macro texture had a lot of flow pass under the tyres to get rid of the water. So it worked very well. And as you can see there, it helped disperse the water. You haven't got those more defined channels for the water to go across. But that's where we're heading off. There's a lot more work to go. 12D and Bill Simon themselves have got to get together, but essentially what it is road designers will be able to model a new road or an existing road. We'll be able to run this over it and we'll be able to get a better picture of all the surface flows, not only on the road surface, but in table drains, etc. So it's a bit of an exciting area to go in, and I don't believe anyone else in the world has done this work before. Thank you.